This first mini lecture for Chapter 6 compares ionic and covalent bonding and explains how the sharing of electrons can lead to a stable bond. As we've previously discussed, chemical bonds form when electrons on two atoms interact by either exchanging electrons or sharing electrons. Exchange of electrons leads to the formation of ions, a positively charged cation and a negatively charged anion, and therefore is the mechanism for ionic bonding. This usually occurs between metals and nonmetals. Sharing of electrons usually occurs between nonmetals, forming covalent bonds, and by the end of this chapter, we'll have a better appreciation for why sharing would be preferred over exchange in certain situations. For both types of bonds, the attainment of a complete octet of electrons in the valence shell of both atoms is a driving force for bond formation. We should now recognize that this octet rule comes from attaining 2 electrons in an s orbital and 6 electrons in p orbitals for the outermost energy level on the atom, or the valence shell. In Chapter 3, we discussed ionic bonding in detail to understand how to determine chemical formulas and names of ionic compounds. Now that we understand a little more about the electrons in the atoms that form these compounds, it may be worthwhile to go back and rewatch that mini lecture which discussed this particular slide in detail. Or you should take a look at section 5.4 in the textbook. In this chapter, we focus mainly on covalent bonding, as the sharing of electrons makes it a little more challenging to understand what is going on with the electrons in these types of molecules. We discussed the forces of attraction and repulsion that occur within single atoms in the last 2 chapters, but now we must think about those forces when 2 atoms are brought close together. The electrons on one atom are attracted to the protons in the nucleus of a nearby atom, similarly to how they are attracted to their own nucleus. And as we've seen before, this interaction is stabilizing and lowers the energy of the electrons, which is a favorable process. However, the electrons on one atom can also be repelled by electrons on a nearby atom, similarly to how they repel against each other within their own atom. And this interaction is destabilizing, leading to a higher energy for the electrons. Additionally, if the atoms are brought too close together, the protons in each nucleus begin to repel against each other as well, which is also destabilizing and leads to higher energies. So, which of these forces, attraction or repulsion, will be most important when 2 atoms come together to share electrons and form a covalent bond? This diagram, referred to as a Lennard-Jones potential graph, shows the energy of 2 hydrogen atoms that start far apart and are brought together to form a bond. Note that when the atoms are too far apart, there is no interaction, repulsive or attractive, between the 2 atoms, and we label their energy as 0 since this represents a starting frame of reference for individual atoms. As the atoms get closer together, the electrons in each atom begin to interact with the protons and electrons in the other atom. Initially, the energy drops as the stabilizing attraction of each nucleus to the electrons in both atoms dominates. This drop in energy indicates that energy would be released by the atoms as they get closer and closer together. Then, we reach a minimum in the energy as the distance between the atoms continues to decrease, and suddenly the energy spikes, going to even higher energies than when the atoms were completely separated from each other by a large distance. At this point, the repulsion between the electrons and protons in each nucleus has become the dominating factor, and the increased repulsion as the atoms get closer and closer together becomes incredibly destabilizing, hence these really high positive values for energy. Note that the positive energies on this diagram represent the energy that is required to hold the 2 atoms this close together. So exactly where would this energy be coming from? Well, if this molecule exists in empty space, then there is no energy available to hold the atoms together. So the atoms quickly return to being farther apart in order to lower their energy and stabilize the system, falling back to the minimum that's indicated here. Therefore, this energy minimum on the curve represents the most stable configuration for the 2 atoms, and therefore it also gives the bond energy that is released when the 2 atoms come together, and it gives the expected bond length between the atoms. Note that this diagram clearly explains why we typically see a release of energy when new bonds are formed, because the formation of a bond leads to a lower overall energy for the atoms involved in the bond. So, when two atoms approach each other, there is a certain distance at which they will begin to be close enough to interact. Initially, the electron clouds on each atom begin to distort as they start to become attracted to the protons in the nucleus on the opposite atom. And then at some point, the electron clouds merge, forming the covalent bond, and the energy stabilizes at a minimum where the distance between the atoms maximizes the attractive forces between the electrons and protons in both atoms, while also minimizing the repulsive forces between electrons on both atoms and protons in both nuclei. Since the electrons will be attracted to both nuclei, the electrons involved in the covalent bond will spend more time between the nuclei of both atoms. So, the space-filling models for a few common molecular compounds are shown below here to emphasize this overlapping effect of the shared electron clouds in the covalent bonds between all of these non-metal atoms. Now, in the early 1900s, Gilbert Lewis suggested that noble gases were particularly non-reactive, or don't like to form bonds, due to the stability of their electron configurations. The electron configuration of a noble gas represents the complete filling of the s and p shells for each energy level, giving a complete octet of valence electrons in the outermost energy level shell. The octet rule focuses only on the s and p subshells and ignores the d subshell, as filled d orbitals are technically part of the inner shells since their energy level is lower than the outermost shell for the s and p electrons that are considered valence electrons. And elements that have electrons in d orbitals also follow something called the 18 electron rule. But that's a topic for a higher level chem course, so don't worry about it for now. Instead, again note this idea that all atoms are trying to achieve the electron configuration of the nearest noble gas, and this explains why metal atoms give away electrons to form stable cations, and non-metal atoms seek to take electrons from other atoms to form stable anions. In covalent bonding, much of this same idea applies, except this time the nonmetals involved in covalent bonding are both trying to take electrons from the other atom, leading to the sharing of electrons between the two atoms. So as long as each atom has 8 valence electrons available to it through sharing, then it's happy to share some of those electrons with the other atom. Electrons shared in a covalent bond come from the valence electrons on the two atoms involved, because they are the outermost electrons on the atom, making them most likely to be attracted to the nucleus of the opposite atom. Therefore, core electrons are not used in covalent bonding and are mostly ignored when creating Lewis symbols and Lewis structures. A Lewis symbol shows the valence electrons for a neutral atom as dots surrounding the atomic symbol. By convention, we place a maximum of 2 dots on each of the 4 sides of the atomic symbol, making it easier to quickly assess how far we are from a complete octet. We also place 1 dot on each of the 4 sides before pairing up the dots. This list below shows the Lewis symbols for all main group elements in the first 3 rows of the periodic table, which will be the elements we'll see the most in this course. Note the valence electron configuration for each, based on its position in the table, and how that electron configuration is represented by electron dots surrounding each of these atomic symbols. Note that the orbitals and energy levels for these electrons are missing in this notation. Note that atoms in a column have the same number of electron dots as they have the same number of valence electrons due to their similar electron configurations. Finally, note that hydrogen and helium are special cases, as they only need 2 electrons to complete the first energy shell because there's only a s orbital in that first energy shell. So hydrogen and helium do not follow the octet rule, but rather follow the duet rule and only need 2 electrons to be stable. In the next mini lecture, we'll see how these Lewis symbols can be combined to create a Lewis structure for a molecule that predicts both the arrangement of all the atoms in the molecule and the number of bonds between each pair of atoms. This concludes the first mini lecture for Chapter 6. Please note any questions you may have about this material and how it is utilized to solve problems in the sapling homework or end of chapter exercises for this chapter. Please post any urgent questions on Piazza. I will also take questions on this material during one of our virtual class meetings, and during that time, we'll focus more on problem solving for concepts in this chapter.